I'm going to speak about a topic which grew out of an American Institute of Mathematics workshop in 2022. And all of the things that I'm going to talk about are joint work. So that's one joint project with Komla Domelevo, Polona, Valentia Fragkiadaki, Ohad Klein, Diogo Oliveira, Silva, Lenka, and myself. Okay, so first let me introduce the notation, because we are going to work in the setting of the Hamming cube, by which I mean the set -1, 1, n. And we'll consider functions, mostly functions from the Hamming cube to the scalars, C or R. Sometimes we'll consider functions which takes values not in C but in -1, 0, 1. Okay, and we equip this set with the probabilistic measure, and then we consider the LP norm to be just so the probabilistic. Okay, and then any function on from the Hamming cube to C can be expanded into Fourier-Walsh series in this manner, so that any f is a sum over the subsets of the first n integers of its Fourier. Yes, f of s, ws, where ws are just the Walsh functions. So ws of delta equals the product of j's in S, delta j. Okay, and then this is the setting that we are working with, and then there are like one more notation that I will need. I try to keep this part of the blackboard not erased, so that it does not disappear. And we'll also consider functions of degree up to d and the tail spaces from d. So the symbol deck will denote the space of functions from -1, 1, n to c, such that in their Fourier-Walsh expansion, only sets smaller than d appear. So this is the set of those f's that are equal to sum of s greater than d, f of s, ws. And similarly, the tail space will be analogously defined. So that, sorry?
Smaller?
Smaller, thank you. Smaller equal, thank you. Yes, smaller equal, and the tail space will be with larger equal. So now this is the set of functions which have this expansion. S greater equal to d, and the same as before. Now, having this Fourier-Walsh series, we can define operators on the functions, and the most important operator for us will be the discrete Laplacian. So this operator is so first we consider discrete derivatives, the usual thing that already appeared in some other talks, just 1/2 f of x minus f, not x, sorry, delta is usually the symbol that I use here. So delta minus f of delta plus j, yes. And that just means that we flip the jth coordinate. And then the Laplace operator is just a sum of delta j's, dj's, sorry. From j equal 1 to n dj. Okay. And this operator has a Fourier-Walsh expansion where instead of ones here we have the size of s. So one can write it in equivalently as the following: LF equals Okay, and by the way, if in this way we define the Laplace operator, then we can define any function of the Laplace operator by, instead of taking s here, taking f of s here. So we'll need like 3 of these functions, so I'm going to write it for a generic function f. So similarly, maybe for capital F, we define f of delta on f. Yeah, maybe f is a bad letter, so let me change it to m. M of delta equals sum of s contained in n, m of the size of s, f of s, WS. So yeah, this is just so if this was the spectral decomposition of the Laplacian, this is a spectral functional calculus for the Laplacian on the function f. Okay, we'll need, as I mentioned, three m's. One of them is here, m equal to x, m of lambda equal to lambda a. We'll also need powers of it and the exponential of it. So in particular we'll take m of lambda equal to lambda to z, where z is a complex number with real part greater than 0, and we also take m of lambda equals exponential. Okay. And if one has defined those functions, then there are 2 trivial estimates on L2 that one can state for z equal 1 here and for the exponential function. So, say Parseval-Plancherel's theorem, or simply orthogonality of the Walsh functions. We can prove the following 2 estimates. That if you take the operator delta, applied to a function, and if you want to compute its L2 norm knowing that the function is in the low degree space, then by definition, by orthogonality of the Walsh functions, you can just write here d times the L2 norm of f. So this is nothing but orthogonality. Similarly, if you want to compute the semigroup over the that's the semigroup x of minus t delta on a function f, it's L2 norm, but now you take f from the tail space. Then, because the frequencies which would appear here start with delta equal with capital S equal to d, you can just estimate with the largest one, which is x of minus td. Okay, so this is just trivial follows from orthogonality. And related to that, there are 2 conjectures from like 10 years and 5 years about the behavior, about similar inequalities, but on LP spaces. So I'm going to formulate those conjectures, and the goal of this talk would be to, say, make some progress on them in some restricted ranges of functions, or in a manner we'll see in a moment. Okay, so let's say the conjectures. Okay, so the first one, chronologically speaking, is a conjecture due to Manor Mendel and Asaf Naor, and it asks about the second inequality in LP. Well, those conjectures that I'm going to speak about actually ask about inequalities of this kind on Banach spaces, but they're already open in the scalar case, so I'm going to just focus on the scalar case. Okay, so the first conjecture I would like to mention is something called the heat smoothing. Conjecture, and this is due to Mendel and Naur. And it asks about this. It asks about the inequality on P. So that for every P, there are 2 constants, capital Cp and small cp, such that the second inequality almost holds as in L2. So let us read this. So for each p has to be between 1 and infinity, sorry. P between 1 and infinity. So the conjecture asks about an existence of universal constants not depending on n, neither on b, such that for all functions which are in the phase space, you have a replacement for this L2 inequality, but the important point is that this constant is universal, this constant is universal, and here you have t times d, not anything else. So there are results, also proved actually in this paper, that we can replace this t with some other powers, but there are worse than what you have here. So it's important that you want to have t times d. Okay, and another two conjectures which were posed by Alexander Eskenazis and Paka Ivanishvili 5 years after this concern the first inequality over there. So I'm gonna also formulate those. Okay, so this is like he's looking, and let's say, yeah, I labeled them Bernstein-Markov type, and let's say maybe. Inequalities. So conjecture 1 would be this. Similar to that one, but as I mentioned, for the operator delta. Okay, so there is, for each p between 1 and infinity, there is a universal constant Cp such that delta f, the peak norm of this, is smaller than Cp times d times the LP norm of f, and this has to hold for f of low degree. Okay, so this is a replacement of what we had there on L2. The only difference is that this constant now depends on p, but on nothing else. So this means that I mentioned now our conjectures. It's not knowing their hold, none of them. So yeah, and the functions take values in C, as I mentioned. And the second conjecture is related to an estimate from below for the semi-group. So this was for the operator, for the Laplace operator, for the Laplace operator on the Hamid cube, and this is was for the Higgs semi-group. But now we can make a conjecture for the behavior of this semi-group from below on low degree spaces. So second conjecture is like this. For every p between 1 and infinity, there are two constants, capital Cp and small cp, such that greater than equal Cp little Cpd f and this has to hold for f in the low degree space. Okay, and actually one can prove that in this generality, if you want to admit all functions taking scalar-valued functions without any restriction, then this conjecture implies the other one. I'm not going to prove it now, but in a way, during the talk, we'll see what I prove of it. So this conjecture implies the other one, but when we are going to restrict to some classes of functions, it won't be so obvious anymore. But I'm going to repeat it later. Okay, so now let's move to what we are able to prove. Are there any questions? Okay, so the first thing I would like to state is a sort of a weak version of the heat smoothing, which is quite easy to prove. And I'm going to tell you what is this conjecture, what is this statement, how the proof works, and then we're going to try to do the same for the conjectures about the behavior of D, especially this one, and see that it's not going to work, but there is a way to amend it. So let me start with a weaker heat smoothing, let's say. So what one can prove? One can prove the following. That for every p, let's call it a proposition, although it's very easy. For every p between 1 and infinity, there are constants sorry, forgot to mention one thing. So, okay. Okay, so let's take P. Okay, so let's take P. And let's take two parameters, theta and epsilon, related to P in this way, let P be infinity, and that theta over P plus epsilon. Okay. Sorry. So for the remainder of the talk, I'm going to speak only about P greater than 2, because some of the results will need to be reformulated then. But let's just focus on this case. So then, in other cases, some of the results will need to be reformulated, but that's not so relevant for this talk. Okay, so we take P between 1 and infinity, and we take L2 here, and take a point in the middle between P plus epsilon and 2. So observe that when epsilon will go to 0, then it will mean that we are closer and closer to P. And this is like the strength of this approach here. I mean, for this conjecture, it won't be really simple because the proof is very easy, but later it will be more apparent. Okay, so let P be here, and let P plus epsilon, let epsilon and theta be given, and let us have this relation between P plus epsilon and theta. Okay, then I can prove this. You take e to the exponential of the mean minus t delta, apply to the function f, and compute its LP norm. Then this is estimated by an exponential factor, depending on p epsilon t times d. So the dependence on t and d is correct here. But we want to be able to get the LP norm here, but something other. So the something other is the L2 norm to the power 1 minus theta times the LP norm, LP plus epsilon, so norm to the power theta. Alright, I think I copied it correctly. Okay, so what does it mean? It means that when we move epsilon to 0, we are almost getting the correct P norm here, but there is this correction with the L2 norm also. So before I prove it, the proof is very easy, just follow some order. Let me just say some corollaries of that. Okay, so there are like 3 easy corollaries that follow immediately from this. Okay, so one is that, as I mentioned, we get the norm P plus epsilon here, but this is the second norm. And the second norm is smaller than the P plus epsilon norm because P is greater than 2. So it means we can replace the second norm here with the P plus epsilon norm, and all these expressions will glue together to the P plus epsilon norm. So, yeah, the first corollary is that I can write it. Okay, so what does it mean? It means that if we are not really aiming at the full conjecture, P to P, but about something weaker, P to P plus epsilon, then we can prove it. At the cost, of course, that this constant is going to disappear to 0 when epsilon goes to 0, which is, well, if not, then we'll be able to prove the conjecture, but I'm not claiming that we are. So this constant C of P epsilon is positive for every epsilon, for example, for epsilon equal to 1, for whichever epsilon, but when epsilon approaches 0, it goes to 0, which means there is no decay here. Okay.
But what if you use hypercontractivity for polynomials of degree less or equal than G? You will get something.
This is just a Hausdorff inequality.
Excuse me?
This is just a Hausdorff inequality.
This is just the Hausdorff inequality.
Without further hypercontractivity.
Yes, this is
So CP epsilon.
Is it interesting to use hypercontractivity?
yes, exactly. With one minus eta, exactly. Right. I mean, what Sasha said, I don't think it's going to prove the conjecture, but yeah, maybe it improves something on the later. Okay.
But you have estimate on CP on the constant?
Excuse me?
Estimate on the constant
It's 1 minus theta, essentially.
1 minus theta. That's just Hausdorff inequality.
Yeah, maybe let's not stop on this because it's really, I mean, a minor thing. So yeah, I hope the interesting part comes later. So okay. So this is like we were saying. This is just Hölder's inequality, and this just follows from Hölder, right? Another point, that if you restrict to functions which take values in -1, 0, 1, then you have proved it, the heat smoothing. Because then all of these norms, if you think a second, then the second norm to the second power is the pth norm to the pth power, and the p plus epsilon norm to the p plus epsilon power is the pth norm to the pth power. You put everything together, you get the pth norm on the right hand side. So if the function is like this, you have what you want. Okay, and let's say we apply it with epsilon equal 1. We can apply it with any epsilon, but I just want to have a universal constant. C of 1 F. Okay. By the way, this is nothing special. This is nothing really new. It's like a slight generalization of the result of Feynman, Mosen, and Oleszkiewicz. Okay, so we have this easy corollaries out of this result, and yeah, since we already sort of agreed that it follows from Herder, I think I'm not gonna really prove it. So the proof of this statement is just using Herder's inequality with this relation. And then what you use that on L2 you have really decay, and you use on LP that is a contraction setting. So this is the only things that you use for proving this. Okay, so now let's try to do a similar thing for the estimate for the operator delta. Okay, maybe let me move the words. So let's try to do the same for the operator L, delta, sorry. So if we try. Okay, so what happens? We just have delta F, LP norm, I apply Herder. And I apply, if I apply Herder, I have delta F here and delta F. Okay, so if F, let's say, again, F is a function in the low degree space. Okay, so this I can estimate by orthogonality, but this is unbounded.
P plus epsilon?
P plus epsilon, sorry. But this is anyway unbounded, so I cannot do anything with it in this way at least. But the point of this talk and of this result of ours is that you actually can walk around it somehow. Let me try to explain to you how. Okay, so let me state the theorem and then we'll try to prove it. It's one of those talks where I can really almost prove everything. Not everything, but most. If I don't mess up with the time. Okay, so let me state the main result of this talk. Let me just write this can be walked around. Okay, and the theorem is this. That, for every p, p and epsilon and theta in this relation, so 1 over p equals 1 minus theta over 2 plus theta. And again, I just consider p greater than 2, but this is also true. Change slightly change statement is true for p less than 2 as well. Okay, so p is equal to infinity, 1 over p is related to p plus epsilon in this manner. Right, and then there is a constant. There is a constant c P depending only on P and epsilon, but not the dimension, such that for all K, okay, I'll tell you in a moment why this K is needed here, we have this estimate. So not only that I can estimate the operator applied to a function f, but also powers of it applied to f in the LP norm. I can write C of P epsilon to the power K here, V to the K here, and then the same product as was, where is it, as was here. Okay, so this is, yes, so again, it's not exactly the conjecture, it's close to it, but it has some interesting corollaries, which I'm going to mention now. So what is written here is that all powers of the operator have these explicit estimates in terms of a constant C of P epsilon that does not depend on, it only depends on P and epsilon. And maybe I forgot to mention again that now, again, F is in the low degree space. So, by the way, one would be tempted to say that one could just prove this for k equal 1 and then try to iterate, but it doesn't work in this case. And the reason is that those constants will be blowing up too much. And I really want to have the dependence on k, and now we'll see why. I don't want to have e to the c to the k squared. I want to have c to the k for some other corollary that will follow in a moment. Okay, so before we will try to prove it, or mostly prove it during the talk, but let me first state some corollaries. And they are similar to those corollaries before. So the first corollary is that, you can replace the second norm with the P plus epsilon norm, and then we will have the estimate for in terms of the P plus epsilon norm on the right. Okay, so just write it. This is the same as before, the same reason. The second corollary is that if I take functions which have values, start in the Hamming cube, but take values -1, 0, 1, then this conjecture is true for those functions. Because then, if this is such a function, and all of this collapses to the p norm as well as before. Okay, so for such function we have and the final corollary of this is that you have the estimate from below, which is fortunately erased. But the estimate from below was similar to the heat smoothing estimate, only that we needed it from below and for low degree functions. So the statement is this, that if you want to control from below, this expression, and now P plus epsilon norm is on this side, and this is greater than C epsilon times, this is probably 1. It's greater than x of minus C epsilon V times LP norm of F, and this again holds for. So let me spend a second on explaining how this implies this one. It's pretty easy. What you do, you just replace f with the exponential function of the semigroup, and then this turns into here. This correctly here. This turns into the identity, but now on the left-hand side, you will have the semigroup x of t delta, and you expand it into a Taylor series and use this. So let me write a line about it. So maybe I will write it here, this is just below the other one. Okay, so group of corollary 3. Okay, so 3 is equivalent to this statement. And this statement just follows if you expand the exponential function in the Taylor series and use the previous. But as I mentioned, it's important that we state the result for all pairs of k because you cannot iterate. Okay, so yeah, maybe write the sentence, use this and now expand. And estimate. Estimate term by term. Okay, so now let me try to spend the remaining 25 minutes on the proof. Or which sketch of the proof. Let's put it this way. Okay, so I'm going to focus on k equal to 1. So in the proof really needs to be carried over for all case, but I think for the main idea it's not important that I take all of case. So it is important to have the result for all case, and in the proof you have to be careful to have the correct dependence on k. But I'm gonna skip this. I'm going just to prove the theorem for k equal to 1. So we focus on k equal to 1. And there are two main ingredients in the proof. So let me write them. Okay, the first main tool is an estimate for the imaginary powers of delta. Okay, and I mentioned the estimate. So estimate on LP for the specific operators. Okay. In a second I will explain what the operators are and what does it mean. And second main tool is complex interpolation similar to the proof of Stein's complex interpolation theorem, but with one twist that we will see inside the proof. So the second main ingredient is complex interpolation. Similar to complex interpolation theorem. With one twist. Okay, so first let me speak 5 minutes about those imaginary powers. What these are and what are the dimension free bounds for those. Okay, so there is a general theory for symmetric contraction operators, which allows you to, if there is a semigroup which is a symmetric contraction semigroup on all LP spaces, then you can define, then you can take functions of this semigroup which remain bounded on LP, and among those functions are the imaginary powers. So this is initially it appeared in the book of Stein topics, but we would like to have explicit estimates for those imaginary powers, and I think first I saw them in the paper of Cowling. Maybe they can be also deduced from Stein's. Okay, so I'm gonna do a little brief of this theory, or mention what result do we need from that. So theory of symmetric contraction semigroups. Okay. And the assumptions are that we have an operator which is L non-negative operator on some L2 of x mu, completely doesn't matter the space, as long as it's sigma finite. And we assume that it is a contraction of all LP spaces. And then there is a general result which says that you can put holomorphic functions over this operator, in particular imaginary powers. So I'm not going to speak about what are these concrete functions, but the implication of this theory is that if you take imaginary powers, then you have an explicit estimate for their LP norms. Okay, can I call? Yeah, I written it. So the estimate is like this. For each p between n and infinity, there is a constant Cp that depends only on p, such that you can estimate the norm in this regard, and there is an exponential factor here. So what I'm writing here is not the best factor, but it's enough for our purpose. So actually, it is known what is the optimal factor here. It's a recent paper of Dragicevic and Carbonaro that they established the optimal exponential growth here for all semigroups, but it's irrelevant for micro. So. Okay, so what only matters for this talk is that this dependence, when p is fixed, this dependence is exponential in u. Okay, actually, when p would be 2, it is a contraction, so this is too wrong, but we don't care. We just care that there is an exponential growth in u. Okay, so this is the tool we are going to use, and now let's. Having this, I can also I can go to the proof, but let me just remind you that by the way, our operator of course satisfies these assumptions. It is non-negative. This can be seen from its spectrum because there is the size of S always, and then it is a contraction because one can prove it. Yeah. Okay. So the fact is that L equals delta satisfies these assumptions. And the above estimates. Okay, and I just recall that we need the imaginary powers and complex powers of delta, so this will be.
This is also the absolute value of u.
It's absolute value of u, sure. Okay. Yes, and I didn't mention where u is, but u is a real number. Right, so delta z is a complex power of the operator, which is just, one can define it like this. Let's say we can take out the empty set because I wanted to put the size of S here. So the empty set would be just 0, and then z S. Okay, so now let's go to the proof. We go with this one. With this one fact from the general theory. Okay, I think I can erase this to get the proof of the corollary. Okay, so the idea is to interpolate the L2 bound with growing powers with the LP bound with no power. And let me maybe write a sentence about what I mean by that. So idea is this. Interpolate something of the sort.
So sorry, are you sure about your exponent in your the angle? So why one is there? You have.
I just added it because I didn't because I mean I wanted to read it from the paper of Michael Cowling, and there is a log in front, but I completely do not care about the size of the growth. So this is far from optimal. It doesn't matter.
Okay.
Yeah, it's like really far from.
You need only a constant.
Sorry?
You need only a constant. You need only some constant.
Some constant, exactly. The optimal is arc sine of something actually. Yes, but I completely don't care about it. So it just the exponential growth is to allow in the complex interpolation more explicitly in the Hadamard's 3 lines lemma that it is admissible on the boundary. And when you have exponential growth, you can cancel it with some Gaussian factor in front. You will see in a moment. So this is why exponential growth is okay with any even. Okay, but the idea is now the following: that I want to interpolate this. Because this just holds. If I have a very good estimate on L2, very explicit estimate on L2. be d to the n. But the problem is that this does not hold for general functions, it holds for functions of degree at most d. So I cannot just use interpolation per se. This is not allowed. So I will need to change something to make it work and to produce what we have. Okay, so this is the idea, now I'm going to execute it. Okay, so coming back to the group. Okay, so we consider now so it is enough to prove this. D F perfect G linear product is controlled by C of P epsilon times D times F second power to minus theta times F plus epsilon power to theta, and this needs to hold for G in LP prime, because now I want to have an estimate for the LP norm of delta F, which means I need to take G from LP prime of norm 1, say. Okay. So for this purpose, I'm going to build a holomorphic function, family of holomorphic functions, and then we will estimate them on the boundaries of the corresponding strips. First, we erase some. Maybe this thing above. So, yes, I'm going to define a holomorphic function, but first I need to take a particular modification of G so that I can use Hilbert appropriately. So, we'll need to first take some modification of G. Okay, so what we take is this. So we take a family of functions GZ, this is the strip, real part of Z between 1 and 0. So I consider the strip from real part between 0 and 1, and I consider a family of functions. This is the usual part of the complex interpolation, as usual, but I'm recalling it because maybe not everybody has seen it. So we take a family of functions G such that when the real part is 0, then what happens is that G Z L2 norm is 1 for real part of Z equals 0, and G Z, which norm, sorry, Q prime norm. One notation I would like to say is that P plus epsilon equals Q prime. P plus epsilon equals Q. So I will not write P plus epsilon, but Q. Okay, so I want the dual norm in the Q prime space is 1 when the real part of Z equals 1. So this is a standard construction. I will not write explicitly what the function is, but this is possible. And it's possible in a way that this function is holomorphic. Okay, and now I'm writing, one more notation. So I set n to be equal 1 over 1 minus theta. Okay, and I write a holomorphic function, define phi of z to be the following holomorphic function. So there is a correcting factor in front, so I can conclude what I want. Z squared n times Z. Okay. And now there is a difference between the usual proofs and the one that I'm doing. I did not put any holomorphic argument in F, because I cannot. And this is why the argument does not work for general functions, because if you modify it in a complex way, you won't be, probably you won't preserve the space of low degree functions. If there is a way to modify it in a complex way that you do preserve the low degree functions, then the proof would work, but I have no idea if there is one. So on purpose, I did not put a complex parameter on the function f. And this is the reason why we are not proving the conjecture. We are obtaining something else. Okay, so this is a family of holomorphic functions. And yes, and because we are, note that we are interested in the parameter, so we are interested in z equal theta. Because what happens when z equals theta? When z equals theta, this is some number, right? That depends only on q, but q depends only on p and epsilon. N is 1 over 1 minus theta, so also depends only on p and epsilon. But this is exactly n times 1 minus theta, and n times 1 minus theta is 1. So we end up with the Laplace operator f applied to g. Okay. If it was the estimate for the k power, I would need to modify the definition of this n. It would need to be k over 1 minus k.
So g of theta is g sub theta is equal to g?
G sub theta is equal to g, yes, forgot to mention this, right? Yeah, sure. Thank you. Yes, g sub theta is equal to g. Right, so this can be done in this way. It satisfies these three conditions. Okay, and then we just apply, yes, we apply what we want to apply Hadamar's three lines lemma, and this lemma says that if you have a holomorphic function, so this is the real part of z equal 1, this is the real part of z equal to 0, then what it says that if you want to estimate a value of this holomorphic function in a point inside here, then it can be estimated by the geometric mean of the maxima of the function here and here. So this is what is called a Hadamar's three lines lemma. Okay, and of course it assumes that the function is holomorphic inside, but we are in a finite world, so everything is holomorphic, everything is bounded. Only that you need to preserve the growth of the constant. So have an estimate that does not depend on the constant. So in particular, this function is holomorphic everywhere. Okay, and we apply this lemma. So after applying Hadamar's three lines lemma, we are left with estimating this function on the line when the real part is 0, and this function on the line when the real part is 1. Those two inequalities, so let me write it. Phi of z smaller than d to the m f L2. So this is the L2 inequality and the L2 inequality. Phi of z smaller than, and now I don't have anything, but I have a constant which is uniform. CPQ times f. So what I'm saying is that if you have these two estimates and apply Hadamar's three lines lemma, then you will get the estimate you want. Because the L2 endpoint corresponds to 1 minus theta. So if you want to get from the L2 endpoint to the P point where we are initially, you have to multiply n times 1 minus theta, and this will be 1 because of the choice of the parameters. Okay, so I'm saying that I just focus on those two inequalities now. Because by Hadamar's three lines lemma, this is enough to conclude what we want. Okay, and one of them, this is just an L2 inequality, so it is going to be really straightforward. And the other, I will use the boundedness of the imaginary powers. Okay, one thing I forgot to mention that is important is that you will not be able to get the LP norm on the right, but you will be able to obtain a geometric combination of the L2 norm of F and the LQ norm of F, which is exactly what was in the conclusion of the theorem. So regrettably I erased it, but okay, something like this. Yeah. So you will obtain this, you won't obtain the LP norm of F. So have you started like usual in the proof of complex interpolation results with changing the F, you will get the LP norm. But you cannot do it here, so you will end up only with this expression, not with the LP norm. But anyway, this will follow if I prove those two inequalities. Okay, so let's first start with I'm almost out of time. So okay, so this is just the L2 bound, which just follows from the fact that powers of the Laplace operator, you have n times 1 minus z, and now this is for the real part. Sorry, this is for the real part of z. Zero, right. So this is real part of z0, and this is real part of z1. So in the real part of z is 0, this is essentially n times 1 minus some imaginary number. And if you're on the degree space, then this will be controlled by d to the n. Because the imaginary powers are contractions, is isometries on it. Okay. So let me say a second about the second estimate for the LQ. So about the LQ. What you do, you recall what this function was. You keep this factor, but now what you have is that the real part of z is equal to 1, which means that there is only the imaginary power here. There is no delta to some positive power, there is only delta to the power minus iu in this case. Okay, so we have phi of z smaller than this constant that was there.
But in your further estimate, you should also have some constant exponential.
Right. This is needed. Sorry, I forgot about. Okay, so
imaginary part of it.
right. So this is putting z squared was on purpose here because when you now compute, say 1 plus iu, then the z squared of this it has the real part 1 minus u squared. So it will compensate with any exponential growth that you get in u. So this is on purpose that there is z squared here. And similarly, if you take z equal to iu, then it will just be minus u squared. And again, it will compensate with the exponential growth. So yes, of course, you need to do it, especially on the LQ endpoint, because the imaginary powers grow. So I'm writing it here. It will be x of minus 1 minus u squared. Sorry, plus 1 minus u squared times the factor that was there. This is now the LQ bound, which means that the real part is 1. And then this expression that was there, which is n pi sorry, this is with a minus, this is with a plus, and this is multiplied by u. But then what I get is, we call that I took it here, so delta to the, no, sorry, I took it wrongly, one less step, sorry. So I have this, multiplied by what I have there, n times 1 over q minus 1 half plus 1. And now this was just coming from the definition. Right? But it goes with a minus u squared. And now what I do, I just take minus delta to the power n I u, because when real part of z is 1, I consider z equal 1 plus I u. Okay? In the definition of the function, it was here, but that means it will be n to the power 1 minus I u minus n I u. And what I do else is I use header, and this header will mean that I will get this q form of this times the q prime norm of the function gz, but gz was made in a way that the q prime norm of gz is 1. So I forget about it. And now I group all these things together. So
1 second, and where delta to the n?
the delta to the n, it comes from here, because in the definition that's delta to the n 1 minus z, and you take z to be equal 1 minus.
Yeah, okay.
Okay, and now I know that this has an exponential growth, but doesn't matter because it's going to be killed by this Gaussian decay. So if I glue it together, I will have an estimate. But there is a, okay, in this process I produce a constant here, which depends on q. Because the bound for the imaginary powers does not have constant 1, but some universal constant. So this is the constant, it depends on q, q dependent on p and epsilon, then, so that's okay for us. Okay, so altogether, this times the norm of this, so now we use the bound for the imaginary powers. Produces another constant, say CQ prime times the epsilon over. So this is what we wanted to have here exactly. So it doesn't matter if I write P or Q because Q depends on P and epsilon, and I'm allowed to have dependence on Q and epsilon. Okay, yes, so this concludes the proof apart from, as I was saying, for k greater than 1, you need to be careful to drag down the dependence, and in particular, the reason that I put exactly this, and like, in this case I could have put anything, it doesn't matter if it was n or something less a constant times this expression will be okay because it will be Gaussian. So decaying, but then to mark the case where k is not equal to 1, one needs to be a little bit careful to choose this n instead of something else. But anyway, putting all the things together, one can have this result. Okay, I think I'm almost over time, so thank you very much for your attention.
I have a question. So, can you say again why you cannot prove the full conjecture?
Because I end up with what I prove is that on the right hand side you have this times this, and I don't see any way how you can go back to the norm from this product.
No, but you mentioned something about approximating.
Switching F to FZ and C.
Right, okay, right. So normally in the proof of the complex interpolation, or say Stein complex interpolation theorem, so that's a theorem about analytic families, about interpolation of analytic families of operators. And in the proof, there are three functions that are analytic. The operator, the function fz, and the function gz. And the proof works if you can make all of these functions analytic. But here I cannot make f analytic because if I try, I don't know, but if I try to do it the usual way, then it will destroy the fact that you are in the less than the degree space.
Okay.
Okay. So if there is a way to do it that you remain in this space, then the proof will work. But I don't see any way to. Normally, the way to do it is just you consider what are the values of the function and you put complex powers above those values and times the signum in front. So it's really easy to come up with what should be the function for this preserving of norms. But doing it in this way completely destroys the Fourier spectrum, and one has no idea if you can recover it back. So yeah, if we forgot about that, if there is no dependence on z, then you cannot go back to the LP norm of f. You will just get this product because you use scalar. But I don't see any way to go back unless you can make analytic families of functions which preserves the degree, which we have no idea if it can be done or not. Probably not. But
You say let's take gz such that g theta is g, and then how to take such gz?
okay, I have a formula. It's like maybe let me set you right. I don't remember exactly, but it's a standard thing to do. So yeah, I can write a formula for that. So maybe here. Okay, so the formula is okay, so let's assume that, so I didn't mention it, but without the laws of generality, we can assume that our functions are real valued. Because if not, you split it into complex and imaginary and real valued. Okay, so this formula for gz is like this. You just sum the characteristics, the indicator functions of points. Signum of g over delta. Then the characteristic function of the point, delta, where I am. And then here I will just put the value of f to an appropriate power. That all goes well. So I'm just going to copy the power from the vector. Okay, so it's like this. It will be g of delta, the power p prime times 1 minus b. Sorry, the power is quite long. So it is going to take the minus z over 2 plus p prime z over 2 prime, and then the characteristic function of delta. So this is made essentially.
It's q prime, probably, right?
Excuse me?
Q prime, yes?
Q prime, right? And q is the p plus epsilon.
It's like there, q prime.
It's like that, q prime. Here, yes, it's a prime here. Okay, so this is a standard way. I mean, it's like even in the proof of Stein, it's almost the same, but I just written it in a different way. So what it means is that because of this signum here, if you take z equal to theta, this will be 1. And this will mean that you just take the function g because I multiply it by the indicator function. I could have said that I just defined it on every point, but I just written it in the summatory way. But if, let's say, z is equal to, the real part of z is equal to 0, then the modulus of this is made in a in such a way that if you raise it, if you want to compute the second norm of this function, you will have something like expectation of g prime. Let's say now z is equal to what? To 0. Okay, let's think what happens when z is equal to 0. So this is 0. So the real part is 0, but only the real part decides about the magnitude of the function. So in modulus, this part does not contribute anything, and this part is p prime times 1 minus theta over 2. This time is p prime over 2, because I said that the real part is 0. And this is p prime over 2, and I was saying that the second norm of this function, when the real part is 0, is 1. And this is exactly what happens, because I started with a function which has the p prime norm equal to 1. So what will I have here is this. P prime over 2 squared. And this is 1. And the same happens on the other endpoint. Okay. Yeah. So I could have done the same with f, but this would destroy, as I mentioned, the degree. So I can't, or at least for this problem. Yes?
So in your argument, have you used the fact this is a hypercube?
No, I don't think anywhere. I mean, only that it's a construction semigroup, and yeah, it has some property. So actually, the only moment where I use that is a degree, it has this property of a certain degree, is where I was estimating the second norm. Unfortunately, I erased it. But there was an expression for phi of z when the real part of z is equal to 0, and this was the only moment where I used some assumption that the function is at degree up to d. So it doesn't really use that it's a.
For example, can you have the same thing for torus?
Maybe I have not.
I think so, yes.
But on torus, the result is even better.
Okay.
Yeah, let's know, right? So, yeah, I don't know if there's any new interesting result from.
More questions?
So how is about the conjecture for some special p, for example, if p is even anything?
We don't
you
know.
This in this case,
4 is normal.
for example, for 4, yes.
No, I don't think that anyone has managed to actually expand and
For 4, everything can be calculated.
principle, but then you have all the cancellations of the world function. I don't think that someone has done it. No.
Can you do it in balance space?
A second. So if the imaginary powers are okay,
There is no signal, of course.
yes. So in Banach spaces, I think one of the problems is that it might not be that if you define the functions and take functions up to a certain degree, then there is some kind of a Planck formula. So that's the first thing. And second thing, you will need to know that the imaginary powers are bounded on Banach spaces. I think this is true on UMD probably, but this probably for UMD spaces would work. But the other part, I don't know what's
Both
Space would have to be
estimate is probably.
I think both inequality require the job.
Some spaces.
Some for sure. Yeah.
So we focused only on this because anyway the conjecture is even open for the scalars. So first let's prove it for the scalars.
Actually, conjecture in Banach spaces is exactly for K convex.
Yeah, sure, of course. Yes, it is for K convex, but it's still not known in the scalars. So
Conjecture is
for K convex Banach spaces.
Okay.
For K convex.
But maybe I have a question. So maybe someone who knows that bundles of imaginary powers, you need UMD, right, for that probably?
It's actually necessary.
Or not? Yeah.
K convexity is necessary.
I don't know about the hypercube, but for
The usual Laplacian. Yeah, I also don't know for the hypercube Laplacian is the UMD necessary for the imaginary. Probably. My guess would be yes, but
You know K convexity.
But I mean, maybe not for the conjecture, but for this method of proof, if you want the boundedness of the imaginary powers, might not be true.
And is there a iteration?
No questions? So if not, let's thank our speaker again.